Welcome to the second lecture of algorithms and analysis. And today we're going to continue on from where we left off in terms of an overview of the three notations that we briefly introduced last time, which was the big O notation, the big omega notation, and the big theta notation. And then we're going to dive into the formal definitions. All right, so once you've had an overview and just got a sense of what those three terms mean, then we're going to go into the formal definitions, and we look at two definitions. One is something which I feel is more intuitive to understand, and then I look at the definition that is there in the book. All right, and that's the more classical definition, which you'll find generally available, but it's a little harder to understand at first glance. So I'll first introduce a formal definition and then the alternative definition, which is there in CLRF. Right? Then, hopefully time permitting, we will go on to another aspect of this course, which is proofs. Right? So when I spoke about the overall, the syllabus, I mentioned that we will be looking at analyzing algorithms. We'll also be looking at proofs, right? And then at a later stage, we'll be looking into design as well, okay? So right now, we're going to focus today on analyzing algorithms, understanding the different notations, and then perhaps looking at an example of conducting proofs using something called loop invariants. So just making sure that you guys have access to the poll everywhere so that you can give me feedback as you go forward. If not, just take a quick snap of that. Otherwise, let me go on. So this is the notation that I'm going to be using for previous slides. So, just make sure that you understand that not all of these slides are on today's lecture. And so in the last lecture, we started off by speaking about the order of growth, right, which is referred to as complexity. And we described different aspects of it. Basically, we said that there are different notations. Okay, so we have the big O, the big theta, the big omega, but all three of these are essentially asymptotic notations. All right, it shows the asymptotic behavior of a function or of an algorithm as n, the input, becomes extremely large. And the usual technique for analyzing these algorithms is that we drop the highest power of n. So if you've got a polynomial function, we simply look at just the highest power, we drop the lower powers of n. We also drop the multiplication factors, all right? And so these were some of the examples that we looked at in the past. And then we looked at a linear search example. Okay, so this was sort of a trivial, simplistic example, and we'll get on to more difficult examples as you go forward in this course, but this is a good example to start with, and it gives you a sense of the basic concepts. So this was a fairly straightforward example of linear search, and then we said, well, if we have this particular algorithm, what is the worst, average, and best case complexity, right? And so we looked at the worst case complexity being for all possible inputs. Okay, so you can think of all possible inputs. What is the worst case situation that this particular algorithm is going to behave in? The best case, we said, is not very useful because, if it's for all possible inputs, you could come up with, your pet case in which the algorithm would behave really nice, but that's not very useful. And it's not very useful in the real world either. All right. And the average case is unfortunately also a bit tricky, as I said, because it depends on how the distribution of the input is, and that's generally not given beforehand. So if you have to make certain assumptions about the distribution of the input. So generally, the worst case is pretty much what we're going to be looking at in a lot of cases, but once in a while, we'll also look at the best case just as a comparison with the worst case. And we'll be looking at average cases maybe later on in the semester. So this was the way we said, how do we do the analysis? Well, we could simply assign costs and times. And since we know that we're only doing, an order of magnitude or an order of the growth rates, so we said that as in the past, We're going to drop the actual constants. We're going to only look at the highest power of n. And so you could actually take these and replace all of these individual costs because they're constants. You could just replace all of those with 1. However, the number of times these particular statements are executed is, of course, extremely critical. All right, so this needs to be there. This can be neglected, so replaced by 1. And so we said that if we do the following, then the best case and the worst case, and perhaps the average case for the linear search can be characterized as follows. The best case takes 4 units of time, all right, whatever the units are, the worst case, but it doesn't depend on n. The worst case does depend on n, the size of the input, and in this case comes out to be 2n plus 4. And the average case, you might guess, if it's uniformly distributed, comes out to be n plus 4. And so then we said, well, how do we express these 3 cases in the more accurate notations of either big O, big omega, or big theta? All right, because expressing it as follows is not very useful. So we need to be able to express each one of these in one of these 3 notations. All right, so that's the whole objective of today's lecture, to be able to understand these in depth. So I started off by saying that the big O notation is essentially an upper bound. All right, if it's an upper bound, then if, for example, you have the function given by the following polynomial, the upper bound can be seen to be if you drop the lower the lower values of n, and we just look at the highest power of n, and then we also drop the constant, then basically we're left with n cubed. And so clearly it's an order of n cube complexity. All right, but when we said that if you're using the big O notation, then big O is an upper bound, which means that even though it makes sense to express it as order of big O of n cubed, you wouldn't be inaccurate to say that it is big O of n to the power 4, right? You wouldn't be inaccurate to say that this is big O of n to the power 5 or any of the higher powers, simply because all of these are upper bounds, right? Similarly, we said the omega notation is a lower bound. Okay, so if you have f of n being given by the same expression, then we again do something similar. We drop the lower powers of n, and we're left with 7n cubed. We drop the constant, and this seems to be the lower bound. Also seems to be, from an intuitive point of view, seems to be omega of n cubed. Now, I haven't really given you the formal definition. So right now, you just, you're getting the sense of what it is about, and you're sort of believing me to say that this is an order of omega of n cubed as a lower bound. Okay? But then what is more important on this particular slide is to understand that since it's a lower bound, you could also say that not only omega n cubed is a lower bound on this function, but also omega n squared and omega of n, in fact, even omega of 1. All 3 of those are lower bounds, although they might be not be very useful lower bounds, right? Simply because they're extremely loose. And then finally, we said that the theta notation is a tight bound, all right? And this becomes very useful in one particular situation that doesn't always happen. But if, for example, the upper bound and the lower bound are given by the same expression g, in my previous slide, I referred to it as f, but it would be better to differentiate that from the actual function. So I refer to it as g. If both of these happen to be the same, then this particular function can be described as theta of g of n. Now, all of this might be very confusing for you right now. So let's go ahead and take a look at a few examples, which might again make it more clarified. So any questions on anything related to the previous lecture? Some of the stuff that I'm going to be covering further, but if not, let's just go ahead. Yeah. Right. So So we'll continue with the overview of these three notations, and then before we dive into the formal definitions. So this was the example that we were looking at in the previous lecture, and we didn't quite get to complete it. And I asked you to sort of try to complete this chart. I don't know if any one of you did, but if not, let's just try to see how we'd complete this. All right, so we already agreed that the best case, which is a constant, would have as an upper bound not only big O of 1, but also big O of n, big O of n squared, and so on. Right? We all agreed on that. We also said that for the best case, which is a constant, the lower bound is also omega of 1. Okay. Now let's take a look at the worst case so that we have an alternate to look at. So what's the worst case going to be if we try to describe it as a big O? What's an upper bound on the worst case? So the worst case is given by 2n plus 4 in the linear search. So can somebody tell me what would be the big O notation or notations for the linear search for the worst case? Any thoughts? It shouldn't be too difficult. What's the worst case for, so it's 2n plus 4, right? And what we've already been doing is what? Somebody else. Besides you guys, all right? Besides a few people that know the stuff, or perhaps know the stuff, but somebody else, somebody from the left side, somebody over here, somebody from, yes, somebody in the back. Sorry? Okay, so O of n. That's one possible description of it. That's one possible upper bound on 2n plus 4. What are other upper bounds? Yes, somebody? Yeah. So C greater than or equal to 1 for all values of C, integers or non-integers. Actually, that would be correct. Okay, great. So we agreed on this. So O of n squared and so on. What about the omega notation for the worst case? Okay, so what's the omega notation for 2n plus 4? Somebody else? Yes. Omega of n and omega of 1, right? So would people agree to that? Well, omega of n, as I said, comes directly from this particular expression, from the polynomial. We dropped it to the constants. And omega of 1, why? Because this is a lower bound, right? So omega of 1 is still, it's a loose lower bound, but it still, nevertheless, is a lower bound on 2n plus 4. Okay. So now that we have figured out all of these, if we go back to the previous expression, which is that the theta notation, if the big O notation and the omega notation share a common function g of n, then you can also describe it as theta of n. So what would be theta of n in this case? Okay, so we've already figured this out. What would be theta of n for the best case? Anybody? Yes? Theta of 1 over here. That's right. And what about for the worst case? What's the theta notation for the worst case? Yes, somebody right at the back. Theta of n. Very good. So, so far it seems like people are following this concept, right? And so the reason why it's theta of n over here is because you have big O of n, even though big O of n squared exists, but big O of n and omega of n, both of them share this function n. And so if they're sharing a function, then that function can be used, that g of n can be used to describe the theta of n complexity. Okay. So if this looks good, we can go forward, right? No questions. Okay. So now can we use the following notation? Can we say that the order of n is the worst case and omega of n is the best case? No? Okay. Does anybody think we can? What about the average case? When you say that theta of n is the average case. So I'm expanding my question to not only include the big omega and the big O, but let's say for average, yes. Okay, so somebody mentioned that for average, yes. So would anybody like to elaborate on that? Why can't we use big O as a worst case and omega as best case and theta, and why can we use perhaps theta as the average case? Any thoughts? Why do you think we can't do that? And I'm not going to stop anyone. Right? So somebody has an idea. Well, people do have the right responses. I'd like to hear them as well, and sort of have a more description on the simple response, no or yes. Okay. So somebody's saying yes. So would anybody like to sort of explain why we can't use this? It's sort of like a revision as well, because we've sort of already talked about it. Yeah. Yeah, so these are actually bounds, right? Especially the best case and the worst case are bounds. So you can't really say that this is the average, okay? We can't really say that we can't really say that that big omega is the best case, and we can't say that big O is the worst case, simply because they're actually bounds and they're not really worst case and best cases. And worst case and best cases have to be separately identified. And when you identify that you're looking at the worst case, then again you can have all three of those notations for the worst case. You can have all three of those notations for the best case, and so on. But what about the average? Some people agree that you could use theta of n to describe the average. Okay, so people do have the right responses over here, but let's talk about the average. Why could theta of n be used? You could still say that theta of n is actually sort of the average case. Any thoughts on that? So we agree that the worst and the best case can't really be used. The bounds can't be used for that. But what about for the theta notation? So the theta notation is sort of a special case, and it says that the worst case and the upper bound and the lower bound seem to be converging, and if they are the same, then in fact the average is theta is in fact the average. Okay, so that's still sort of loosely speaking, but yes, you can use the following notation, that you can say that theta of n is the average, but the following two statements are clearly wrong. Okay, but they are used in the literature. Okay, so you might actually, I might have said that as well in 210, but to be accurate, those two statements would be in fact wrong. Okay, in a very loose manner, they can be referred, but accurately speaking, in this course, they'll be considered completely wrong. Okay. So now we've talked about three notations, and those are big omega, big theta, big and so on. What about the small notation? So we do have small o and small omega. We don't have small theta, but we do have a small o and small omega. So yeah, I guess people no clue, right? So I'm not going to spend too much time on that slide before we get something really weird. So so here's what small o and small omega. Okay, so small omega looks like that. It doesn't look like the big omega. That's Greek for you. And small o does look like the big O, but it's just smaller. Sometimes it's hard to figure out. But these two notations are useful sometimes, although practically speaking, we're not really going to be talking much about them, but it's good to be able to differentiate them from the big notations, and once in a while we will refer to them. All right, but practically speaking, they're not used that much. So the basic difference between the big and the small notations are that it's a very simple difference. All right, so if the big O can be considered to be an upper bound, okay, less than equal to, so if f of n is order of g of n, then basically we're saying that order of g of n is an upper bound, or f of n can be less than equal to, okay? But if you're using the small notation, it's strictly smaller. So if you say something, so f of n is small o of g of n, then f of n is strictly smaller than g of n. Okay. Similarly, for omega, this is strictly bigger than. Okay. So it's sort of a small variation of these two. Okay. By simply replacing the greater than equal to sign by the greater than sign, and the less than equal to sign by the less than sign. Okay, small difference. However, if you look, and this is an interesting chart over here, when it comes to describing the behavior, it does become important. All right, so given this understanding of the small o and the small omega, can somebody tell me what would be the, for example, for the best case? We already know that we've already done all of this. Okay. Now, what about for small o? What would be the small o notation for the linear search? Okay, for the best case. Remember, this is the best case for the linear search, and we're saying what could be a possible notation for the small o, given that it has to be strictly less than. Yeah, strictly less than. Sorry. I'm sorry. So small o is bigger than. I got that wrong. Right. So small o has to be strictly bigger than yes, than the function. Right. So small o of n. Very good. So it would be small o of n. Is that it? Small o of n squared, and so on. All right. So the only term that we've been neglecting is the first one, right? So because this one, this is not strictly bigger than the function f of n, right? So similarly over here, what would be the small o notation in the worst case scenario? The worst case is 2n plus 4, or it would be the small o notation. 2n plus 4 has to be strictly smaller than the big O notation. So what would that be? Anybody? N squared, yeah. So small o of n squared. What else? Small o of, yeah. You could write C plus 1, and then you could define it, right? So yeah, you could do that. But I'm just giving you some examples, and you could simply say that it is small o of n cubed, and so on, right? Yeah, you could do that. What about for the omega notation? Okay, so let's do this one first. What would be the omega notation for the worst case? So 2n plus 4 has to be strictly, it has to be greater than the omega notation. So what would that be? Yeah. Small omega of 1, right? So it can't be small omega of n, right? Because that wouldn't be strictly smaller than. What about for this particular case? Yeah. Doesn't exist. Yeah, doesn't exist. That's because the worst case, the best case is already a constant. You can't really do better than constant, right? There's nothing like negative. Right? It would be nice if that existed, but it doesn't exist, right? So basically, this is what we have. All right. So basically, if you have theta of n over here, omega of n over here, then the small omega would be something smaller. All right. And if you have theta of 1, and similarly, the small o notations would exclude this particular value, and it would take all of these values and so on. Okay. So hopefully people have an idea of the small o and the small omega notations. Right. So now you've got hopefully an overview of the notations. Now we're going to go into a more formal definition of big O. Okay, and then we'll look at two possible definitions, and then we'll go forward with the omega notations. So what is a formal definition? The formal definition, which is often found, which is not the one that is there in CLRS, is as follows. So f of n is going to be equal to the big O of g of n, some function g of n, if and only if there exists positive constants c and n naught, positive constants Cn and n naught, such that 0 is less than equal to f of n is less than equal to c times g of n for all values of n greater than equal to n naught. Okay, quite a mouthful. So let's try to understand this by looking at this particular picture graph over here. So here's function f of n. We're saying that this is bounded. The upper bound would be g of n if a positive constant existed c, such that if you multiply g of n by c, in other words, you scale g of n by c, then for some values, for all values of n greater than n naught, all right, so you can see that n naught is over here where it crosses over. For all values of n greater than n naught, c of g of n would be equal to or greater than f of n. Okay, so you can see that in all of this, for the rest of n, for all n greater than equal to n naught, you can see that hopefully c of g of n is going to be greater than f of n. All right, if that is the case, if you can find these constants c and n naught to satisfy the following condition, then you can say that f of n is big O of g of n. Okay, so that's one formal definition. And now we're going to sort of drill down and take a look at a few examples so that we can actually completely understand what this is. So let's take a look at an example. So let's say f of n is 3n squared plus 36. Okay. So our guess is, we already know this, that this is going to be big O of n squared, right? It's going to be big O of n cubed and so on. But now we need to do a formal proof. We have to make sure that we can satisfy this particular equation. In other words, we can find some values of c and n naught that satisfy the following condition. All right. So my question is, can you give me some values of c and n naught that would satisfy this condition? And c being extremely large and n naught being extremely large, yeah, you could do that. So here's a great example where somebody's just picked huge numbers, and that's true, right? Why is that true? Because you've made c extremely large, and you've made n naught extremely large, and that would be the trivial, the simplistic way to do it. But can you find smaller numbers, right? So what would be the smallest set of numbers, let's say, that would satisfy those conditions? Because that sort of gives you a better handle of what we're talking about. So somebody's suggesting C, 3 and 36, okay? There are other suggestions, 3 and 36 and so on. So let's try to solve this. And let's say what would be the possible values of C, the smallest value of C that would satisfy this. So some people have suggested 3. Could we pick 2, for example? Would C is equal to 2 work? Any thoughts on that? Could you pick C is equal to 2? Or could we even pick C is equal to 3? So people have suggested. So, for example, could we pick C is equal to 2, and why not? Somebody's shaking their head. Why can't we pick C is equal to 2? Yeah. Sorry, the lady behind you. Yeah. Yeah. So as n becomes larger and larger, clearly 2n squared is at some point, even though you could pick a really large value for, you could change this, but at some point, 2n squared is never going to be greater than 3n squared as n becomes larger and larger. Okay. So let's pick a value of, so I've picked a value of, let's say C is equal to 4. Let's try to solve this. So let's say we pick C is equal to 4. All right. So let's say C is equal to 4. Now, the next question is, what would be the value of n naught? Okay, but because n naught now needs to be very specific. we don't just want n not to be a million, right? We want to be able to say, well, for all values of n greater than n naught, and for c, let's say we've picked a particular value of c, we want to pick a value of n, the smallest possible value of n naught, so that this condition is satisfied. All right, so how would we solve that? Well, hopefully it shouldn't be too difficult. All we need to do is set 3n squared plus 36 is less than equal to 4n squared. All right, so clearly n squared is less than equal to 36. And so n is going to be greater than equal to square root of 36, which is 6. All right, so hopefully people can follow that. If we pick c, so one possible combination of c and n naught could be c is equal to 4 and c is equal to 6 and n naught is equal to 6. Okay, so that condition would hopefully work. So somebody had suggested c is equal to 3 and n naught being 36. Would that work? C is equal to 3 and n naught is equal to 36. So is 3n squared plus 36 less than equal to 3n squared for all values of n greater than equal to 36? Does that make sense? No. Yeah. So this answer was wrong. So clearly you can see that for any value of c less than equal to 3, you're going to have a problem because you have 3n squared over here, right? So this sort of giving you an intuitive feeling of what combinations of c and n naught would make sense. Okay. So, but are those the only combinations? Clearly not, right? So we could pick c is equal to 4. We could pick a bigger value of 4. So here is something that I've already worked out. But let's say if you plotted this, okay? So I've plotted the previous equation. You've got 3n squared plus 36. This is the original, the blue line over here is the original f of n, okay? And I'm plotting 4n squared from my previous value. So I've picked c is equal to 4 over here. And I'm plotting 4n squared. And you can see that at some point, as n becomes larger and larger, 4n squared becomes larger than 3n squared plus 36. Okay, and so we can clearly see that the crossover point happens at n naught is equal to 6, and so these two numbers make sense. Okay. So, but are those again the only combination? So let's say what happens if you pick c is equal to 5. Okay. So how would we solve that? So let's say we have 3n squared plus 36 is less than equal to 5n squared. So what would n naught be in this particular case? Okay, is that easy to find out? How do you figure out what n naught is? So I'm picking c is equal to 5 over here. And we can try to solve this, but it doesn't seem to be too easy, right? So we could have 2n squared is less than equal to 36 divided by 2. So n is less than equal to square root of 18, right? So not so bad. So, and I think square root of 18 comes out to be about 4.2, which I worked out. So here's an example of how if you use 5n squared, okay, this is how it would show up. So here you can see that if you change the coefficient of the change c from being 4 to 5, the slope changes, okay, and the value of n naught becomes smaller. Okay, now even though the value of n over here is 4.2, but remember that we generally pick integers for c and n naught, and so n naught in this case would be 5. Okay, because for n naught being 4, it's not really crossing over. For n naught is equal to 5, these do cross over. Okay, so those are two possible combinations of c and n naught which would satisfy this particular condition. But we earlier said that you could also use order of n cubed. Okay, So if we said, well, if you want to prove that this particular function is also big O of n cube, then what could be the possible values of C and n naught? And how would we find those? Okay, so basically what we're saying is that we need to make sure that 3n squared plus 36 is less than or equal to some value of C n to the power 3. And this has to be true for all values of n greater than or equal to n naught. Okay, so again, you could pick some numbers out of a hat, and you've probably got a good idea that if you picked 1 million for C and 1 million for n naught, it would work, right? But let's try to see if smaller numbers can be used to satisfy that. Okay, so what would be the smallest value of C that would satisfy this equation? Smallest value of C that would satisfy this? Well, we've got n cube on this side, all right, and n squared. So, and we're simply saying, well, we want the right-hand side at some point to be able to become larger. So C is equal to 1. So people are suggesting C is equal to 1 would make sense. Okay, so clearly if you chose C to be equal to 1, then at some point n cube is going to be larger than n squared. Okay, 3n squared. Okay, but now the question is, how would we figure out what n naught would be? Okay, so we'll talk about the set of functions when we, this question over here about the set of functions. So yes, we will be talking about the set of functions when we talk about the CLRS definition. Okay, just hold on to that thought. Yeah, so people are giving the right responses. So let's see that if you want to satisfy this with 3n squared plus 36 is less than or equal to 1 times n cubed, how would we find out n naught in this particular case? Okay, is this something that we can easily do? Any thoughts on how to solve this? How would we find out? So it's a polynomial equation in the third power. You've got an n cube over there, you've got an n squared, and you've got 36. It doesn't seem to be that trivial, does it? Right. So even if we set it to be equal to, we have to find a value of n where 3n squared plus 36 minus n cubed is equal to 0. And that may not be that trivial to find out when that happens. Okay. But since we're looking for n naught values which are integers, right, simply, then what you could do is simply take different values of n naught, okay, and see whether the left-hand side over here becomes less than or the right-hand side becomes larger. Okay, so you could start with n is equal to 1. Well, that's not going to be the case. It's not going to be true for n is equal to 1. You could take n is equal to 2. Well, 2 cubed is 8, and that's not going to be greater than 36. So you could take 3 and so on. And so eventually you'd find some number where that happens. Or the other way is that you could simply plot it. Okay, so I've plotted these two, and I've plotted n cube over here. All right, and I've plotted 3n squared plus 36, which is the same old function. And you can see that at some point between 4 and 5, these two cross over. Okay, and if you put in the value of n is equal to 5, with c is equal to 1, you can clearly see that 5 cubed, which is 125, is greater than 3 times 5 squared plus 36, which is 111. Okay, so these two combinations would work. All right, let's see if somebody had that right. So you had 1 and 5. Okay, great. So somebody did have that right. For this particular example, in fact, both of those were right. The first one and the second one, third one. So those combinations would work. Okay, and so essentially now we've formally proved that this particular function is order of n cube as well. Okay, that's sort of the formal proof. Now let's take a look at the alternative definition, which is something which is done classically in books as well. Okay? So the alternative definition of the big O function is that for a given function g of n, big O of g of n is the set of functions f of n such that there exist positive integers. So it's fairly similar. There exist positive constants C and N naught such that 0 is less than or equal to f of n is less than or equal to C times G of n. So the rest of it is similar, except that now we saying the same statement in a slightly different way. We're now focusing on O of the big O of G of n. So earlier we were saying that, let's say we had a function f of n, given f of n, can we find the big O equivalent of that? Okay, so you're going from f of n, going forward to finding out O of G of n, right? Now here in this definition, we're going backwards. So here we're saying that, let's say we have G of n, okay? Let's say we have order of, let's say, n squared, okay? The big O of n squared. Now, can we find out all the functions, the set of functions which satisfy this particular property, okay? That f of n has to be equal to, let's say, big O of n squared, all right? So now we're saying that the big O is actually an infinite series of functions. It's a set of functions, right? And here's a more formal way of saying the same thing. So we're saying that the big O of G of n, for some function given G of n, is equal to the set of functions such that there exist positive constants C and n naught, such that 0, this particular condition is satisfied. Okay? So now we're saying that the big O is actually a whole series of, it's a set of functions. So the next question is that, let's say that I'm giving you G of n to be n squared. Okay. So I want you now to be able to tell me what are some examples of big O of n squared. Okay, so clearly n squared is right. Log of n. Okay, small of value of n. So remember, we're basically saying that if f of n is equal to big O of n squared, then f of n, all of these, the order of n squared has to be an upper bound. Okay, so people are suggesting log of n. So here we have a bit of a problem. We've got some people suggesting higher powers of n. Okay, n squared, n cubed, n fourth, and so on. And on the other hand, there are some people who are suggesting smaller powers of n, so log of n, n, and so on. So there seems to be a diversity here in terms of responses. So how many of you feel that it should be n and higher powers of n? So let's hear those guys first. Just raise your hands. N squared and higher powers of n is that set of function. Okay. How many people believe that it should be n squared and lower powers of n? It seems to be equally divided, perhaps. There are more people who are sort of leaning towards the lower powers of n. So think about this. It's not completely intuitive, all right? And sometimes it is confusing when you look at it this way, and that's why I didn't introduce it initially. I first wanted you to understand the simple version, which is going from f of n to order of n. But now, since we're going backwards and we're saying now order of n squared is now a set of functions where f of n is now going to be, so f of n, so this is a whole set of functions, and now we want it, so we want f of n, we want it to be, to satisfy this equation, okay? So let's take a look at this. Well, we're essentially saying that the order of n squared will be the following functions, okay? So we're saying that 3n squared plus 36, clearly this was an earlier example. So we know that 3n squared plus 36 is an order of n squared, all right? But what about n? Is this an order of n squared? Right? Clearly it is, all right? What about 4n minus 100? Okay, that is also clearly an order of n squared. All right, but n cube is not an order of n squared. All right, so the people who were thinking of the higher powers are unfortunately wrong, right? So you just have to figure this out, and if you can't figure it out right now, just think about it. Spend some time and figure this out. It shouldn't be too difficult. Okay, so now the question is, this notation, it seems to be a little confusing for a set notation. So when we say that 3n plus 4 is equal to order of n, people who are mathematicians, is that the right notation? Is an element, right? So the right way to say it would be 3n plus 4 is actually an element of big O of n, right? Why? Because big O of n is actually a whole set of functions, right? And it would be incorrect to equate those two. So this is, but we've been using it all the time, right? So why is that? Well, it's a convenience. All right, so sometimes mathematicians and people who, maybe application people who are computer scientists, try to make life simple. And we don't always use the following element of, right? But what we really mean to say is that when we say f of n is equal to big O of g of n, what we really mean is that f of n is actually an element of that particular set. Okay, but however, we will write it as following, simply because we want to make our life simpler. Okay, and that's the convention that's been used throughout, and that's how the books, you'll see it all over the place, right? Nobody actually uses it as follows, except perhaps somebody wants to be very particular. Okay, so hopefully that is clear, and sort of this goes back to one of the earlier questions that somebody had is, shouldn't O of g of n be a set of functions? So yes, it is actually a set of functions, and hopefully you can see why. Okay. All right, so we've gotten over this particular example, the big O, and we've gotten over. And if you've understood the following, the above two examples, the above two scenarios, the rest of it should be fairly straightforward, okay? But it's important to be able to understand the first two, and if you understand the first two, then the omega notations, the big omega and the big theta will be clear. If you don't understand the above two, then you're just going to run into problems with the other two notations. So let's take a look at the big omega notation. Okay, so it's fairly straightforward, except that now instead of being an upper bound, it's a lower bound. All right. So some of the so earlier it was f of n was less than equal to c of g of n. All right. But now we've simply swapped these around, and now you have c times g of n has to be less than equal to f of n for this to be true. So if f of n is big omega of some g of n, if that's going to be correct, if and only if there exist positive constants c and n naught such that 0 is less than equal to some c times g of n is less than equal to f of n for all n greater than equal to n naught. Okay, so again, this was our earlier example. Okay, so this was the big O notation where f of n was smaller than c of g of n, and now c times g of n is actually on the other side. C g of n is actually smaller than f of n. Okay, so now f of n is bigger. So c times g of n is now a lower bound for all values. It's smaller than for all values of n greater than equal to n naught. Okay, so we found some n naught where that's going to be true. So that's sort of a formal definition. And let's again use our same old example of f of n being 3n squared plus 36. And let's say, well, can you find c and n naught values which satisfy this equation? Okay, so again, we're going to guess that this is omega of n squared. All right, we already have an inkling that this is going to be true. All right, so if this is omega of n squared, then can we find values c and n naught that satisfy this equation? Okay, so people are suggesting 3 and 0. Okay, 0 and 0. So 0 and 0. You have to pay attention. All right, so positive constants, 0 is not positive, so unfortunately. So you can't pick 0. It has to be positive constant. So pick, let's say if you're picking integers, you can pick 1 and going forward. All right. So can future lecture slides be posted before class? So I did respond to some of you. The reason why I don't post future slides beforehand is simply because I want you guys to think. If I gave you all of these slides beforehand, you wouldn't be thinking you would actually know the answer, and I want you guys to think. Okay, so generally I don't give out slides until after the lecture. So let's take a look at this. Can you find out some values of C? So let's see. Well, suggestions coming in are 3 and 1. Let's say. Let's take a look at this. Would this work? So would 3n squared plus 36 be greater than equal to? So we have C of g of n has to be greater than. So the question is, can we write it as follows? Okay, is 3n squared plus 36 greater than some cn squared? And what is being suggested is, let's say 3. Okay, so 3n squared plus 36 has to be greater than equal to 3n squared. And that seems to be almost trivially true, right? What would n not be in this particular case? What is suggested over here? 0. Okay. So I wouldn't use 0, but n not being a positive integer, so we could say this is true for n is equal to greater than equal to 1. So in other words, if c is equal to 3, then n naught is equal to 1. Okay, simply because you have a 36 over here. What other values would satisfy that? Can you think of other values? So people had other suggestions. What about smaller values of 3 or larger values of 3? Could you use c is equal to 4? Could you use c is equal to 2? C is equal to 4. Could we use that? 4n squared. Would that be true? C is equal to 4. Okay, so we're basically saying that would C value of 4 work? Would value of 4 work? Eventually, 4n squared is going to become larger, and so that's not going to work. What could work is any value of maybe 3 or smaller, right? So you could pick C is equal to 2, for example. And so if we did that, let's see what would we get. Well, C is equal to 3 is fairly straightforward, and you could pick smaller values as well, and you could solve that as well. Okay. So here's a plot of 3n squared, and you can clearly see that for all values of n greater than or equal to 1, this condition is trivially satisfied. In other words, 3n squared is actually smaller than f of n, right? So this particular case is satisfied that Cg of n is smaller than f of n. Okay. Right. So let's look at the alternative definition. Again, very similar. And here we're basically saying that the alternative definition is that, yeah, I have that right over here, I think. Yeah. And can I explain what, sorry, for which case? For n not equals to 1? Well, basically what we're saying is that for any positive integer, so essentially what we're saying is that 3n squared plus 36 is going to be greater than or equal to 3n squared, all right, for all positive values of, for all values of n greater than 0, in fact. Okay, so you can see that if n is equal to 1, all right, so 3n squared plus 36 is certainly greater than equal to 3n squared for n is equal to 1. Right? And for n is equal to 2, this is going to be true as well. So simply because you've got 36 over here. Okay. And if you look at the plot, hopefully that becomes clear as well. So you've got 3n squared plus 36, that's always greater than 3n squared. Okay, simply because 3n squared plus 36 has an offset of 36. All right, so it's always bigger than, for all values of n, actually it's actually bigger, for all positive values of n. Okay, so we can pick n not to be one positive integer. That works. Okay. So now let's take a look at this. We're basically saying that in this case, again, in a very similar way, we're saying that for a given function g of n, I did get a few mistakes over here. So omega of g of n is a set of functions f of n such that there exist positive constants c and n naught such that 0 is less than equal to c times g of n is less than equal to f of n for all n greater than n naught. In other words, this is a lower bound on f of n. Okay, and another way of saying that is that omega of g of n is equal to the set of functions f of n such that there exist positive constants c and n naught such that 0 is less than equal to c times g of n is less than equal to f of n for all n greater than n naught. Okay, so again, can people give me examples of g of n if g of n is equal to n squared, right? So what would be the set of functions omega of n squared? So earlier we said that if g of n is n squared, then the big O of n squared would be the set of functions, and we went over that, right? So you remember that. Now, what about for the omega notation? Omega is again now a set of functions, and what would that be? Okay, so starting with, let's say, n squared. So this is a set of functions. Yes, sorry, I'm sorry. So you're saying this would be n squared, right? It would be n cubed. And it doesn't just have to be n squared, n cubed. It could actually be a whole, it could be any function that you can think of, as long as it has an nth power of n, which is what? Which is at least 2, right? So you could have n squared plus 2n, etc. All right, so you can just imagine all the functions that you can think of. They could have logs in them, they could have fractional powers and so on, but as long as the highest power of n is greater than or equal to 2. Okay, so you could have n cubed and so on. So hopefully now you understand that there are two ways of defining the big O notations. One is to say going from f of n to big O, and the other way is going from big O and saying, well, this is a whole class of functions, and what are the possible classes of functions? In which case, to be more accurate, you would say that f of n is an element of either big O or big theta or big omega. So hopefully, if you've gotten over these two, the third situation should hopefully not be too difficult, right? So let's take a look at this particular scenario. So now what we're saying is that earlier we said in the big O notation, you had f of n is smaller than or equal to some function c of g of n, all right? And earlier for big omega, we said that f of n is larger, so c of g of n was smaller, all right? And now, sort of, you can guess that we're basically saying that we have now two separate constants. We've got C1, okay, and we've got C2, right? And we're using the same function g of n. And basically what we're saying is that can we find some positive constants C1 and C2, such that if you scale them, if you scale G of n by C1, then that function is going to be smaller than f of n. And if you scale the same function G of n by C2, it's going to be bigger than f of n for all values of n equal to n naught. All right, so we're saying after some point n naught, this set of functions is going to be greater than f of n, and this is going to be smaller than. All right, so now the trick is to be able to prove that, if f of n is theta of g of n, we must be able to find C1, C2, and n naught which satisfy the above condition. Okay, that C1 g of n, right, is less than equal to f of n, is less than equal to C2 g. Yeah, I've got that right. Okay, so let's see. Let's look at the same function, 3n squared plus 36, and see, can you find values of C1, C2, and n naught which satisfy the same equation. Okay. Hopefully that shouldn't be too difficult. So 2, 3, and 1. So the suggestion is 2, 3, and 1. Okay, will that work? Another suggestion is 1, and 5, and 10. Right. So let's take a look at the first one. So you're basically saying that 2n squared. Okay, so 2n squared has to be less than equal to 3n squared plus 36, and has to be less than equal to 5. And basically what we're trying to find out is omega of n squared. So we're saying 5n squared or n greater than equal to 1. So this is, I'm looking at the first situation that somebody had suggested. So is this true? 2n squared is clearly less than equal to 3n squared plus 36 for n greater than equal to 1, but both conditions have to be satisfied for n greater than equal to n naught. So let's take a look at the second condition. 3n squared plus 36 is less than equal to 5n squared. We've already proven that. So, but is there a problem with this value? Can somebody see a problem with? So I'm not looking at the rest of the cases, just focusing in on this. Is this true? Why not? Somebody shaking their head. Why not? Where is the problem? Problem here, is the problem here, is the problem here? Yeah, somebody else? Yes. Well, anybody, I guess it's quite obvious. Yes. So if we use C2 is equal to 3, so did I get that wrong? Looking at 3n squared. Yeah. Sorry. Yeah, I looked at the wrong figure. Yeah, I'm looking at this. So I'm looking at this particular case. So C2 is 3 times. So would this work? So you're saying that 3 would not work. All right. And that's something we've already covered. So clearly there's a problem over here. All right. And so this one is clearly wrong. Let's say if we change that to 5. Okay. Would that work for n greater than equal to 1? So here the suggestion is actually 10. All right, so let's change that to a 10. That would clearly work, I think. Yeah, because I think we've earlier already seen that that works when you have the following case. Where did that go? Had that somewhere. That works for yeah, I don't know where that went, but clearly that can be perhaps shown to be correct. Okay, so it's going to be 5n squared, where n is greater than 10. So you have 100. 500 is clearly going to be bigger than 3n squared plus 36. Okay, so this is correct. So you can see that this particular expression, you can find C1, C2, and n naught which satisfy the following which satisfy, sorry, not, which satisfy theta of n squared. We have some mistakes over there. So if you want to say that f of n is theta of n squared, then clearly you can find C1 and C2 and n naught, and in this particular example, 1, 5, and 10, which would satisfy the following condition. Okay. So let's take a look at some of the other suggestions coming in. C1 is equal to 2, 4, but you can work those out and see, well, whether they all work or not. Okay, but you can, if as long as you find one set of values, C1, C2, and n naught, then you basically proven that f of n is theta of some function, let's say n squared. Okay, so here what I've done is I've essentially plotted those two cases, and I've said that here is your function f of n, okay, which is 3n squared plus 36, and we've got a lower bound where we're using 3n squared, okay, and you can clearly see that this works. And here you have the upper bound 4n squared, so this is 4, but n naught has now can't be 1 anymore, because we're not only trying to satisfy the lower bound condition, but we're also trying to satisfy the upper bound condition. Okay, and the upper bound condition requires that n naught has to be equal to at a minimum 6. Okay, so n naught has to be equal to 6 for us to be able to satisfy both the conditions. Okay, so so now essentially what we've done is we've been able to see that for this particular equation, 3n squared plus theta plus 36, this is in fact omega theta of n squared. I do have some mistakes. I'll correct those in the slides that I posted. Okay, so and if you look at the alternative definition, then again it's fairly straightforward. Again, you have theta is now the set of functions. So for a given function g of n, theta of g of n is a set of functions such that it satisfies with positive constants c1, c2, and n naught, such that this particular condition is satisfied for all n greater than or equal to n naught. Okay. So can now people suggest what could be if g of n is n squared? Okay, what would be the theta n squared, that set of functions? Any examples of those functions? So if you've understood that theta of now n squared is now a whole set of functions. Earlier we saw the set of functions a big O of n squared. We saw omega of n squared, and now we're trying to see theta of n squared. Okay, the big O was all powers of n squared and higher. The big omega was all powers of n squared and lower. So where do you think we're going with theta of n squared? What set of functions would satisfy theta of n squared? Sort of your intuition. Yeah. So it has to be n squared, right? So you can't have lower powers or higher powers. You have to be exactly n squared. It can't be n to the power 2.1. Okay? It has to be exactly n squared. So the only functions that would satisfy that could be n squared. It could be 2n squared plus 3, or alpha n squared plus beta. Okay, and alpha beta could be any constant. So that set of functions would now be considered to be theta of n squared. And so basically the idea is that this set of functions is exactly going to have the same rate of growth. Okay. So these are the set of functions that satisfy. These are some examples. Okay. So we're almost out of time, but the last point was where we started off from when we defined theta, and we said that if this following condition is true, then f of n can be described as so let me write that over here. So f of n is going to be theta of g of n if the following are true, if f of n is big O and omega. We've already seen that. Okay, so this is sort of a final comment on this particular theorem. So you will see this theorem as well.